Hello everyone and welcome to the second lecture, which is about DSM generation using dynamic programming. In the previous one we talked about DSM generation or image matching using least square method. Today we are going to talk about DSM generation using dynamic programming. The outline of this lecture will be start with introduction, then dynamic time warping. After that I will show a numerical example and I will finalize it with conclusion. Let's talk about dynamic programming. Dynamic programming is a global optimization algorithm and finds the solution of the optimization problem efficiently. Actually, it has been introduced in the 1950s by mathematician Richard Pullman. The dynamic programming is divided the problem or the main optimization into subproblem, and then finding the solution of this subproblem will lead to find the solution of the main problem. One of the algorithm of dynamic program is dynamic time warping. It's used actually in speech recognition. In fact, it's based on detecting or matching based on the similarity of two time series or two paths. For example, if we have two paths or two speech or two image lines, what we will do, it will match between them based on the similarity or similar forms. For example, here this Euclidean matching, as you can see here, it's just matching the sequence of the number or on the time series. But here it will search for the similar or minimum based on the minimum cost and then finding the solution. It has been shown that it's very effective. Actually, in image matching, it will first comparing the gray value, because the image is consists from gray value, the pixels is consists from gray value, and what it does, for example, it matching along the epipolar line each pixel individually from their left and right. The basic idea of dynamic time warping is to identify the minimum cost path, which is used to find the corresponding point. Because as you know, if we find the corresponding point, we'll be able to find the object coordinate. Dynamic time warping can detect not only the corresponding point, which is it's considered to be very efficient or effective point. It can find the occlusion area or occluded pixels, which is very useful to be used in building boundary extraction. As you can see here, we have left and right image. The left image, the camera is here. When the building is captured, a part of the building will be occluded, while in the right image, the other part of the building will be occluded. This means we cannot find, for example, for the point for L circles on the right image, which because it's being corresponded. This is very useful in building boundary because it tells us which one of the building is occluded. The occluded happens when there's a depth discontinuities or there's a change in the height. As you know, if there's a building, there will be a ground and there's a sudden change at the boundary of the building or at the walled area. Therefore, this will be occluded on one of the images. Therefore, the dynamic programming tells us that the location of the occlusions, which later we can be used for the building boundary extraction. As you can see here, this is the perfect match, the black dots, while the blue one, it tells us because it couldn't match the point, and therefore it will be considered as occluded or building boundary. And actually, this dynamic time warping is matching the images globally, not individually. Therefore, it doesn't need to extract the feature point like least square method. This is the match point, as you can see here. This left image and this right image row, just this one row, not the whole of the image, just one row of the images. As you can see here, this the first pixel, it can match with the pixel or first pixel to the on the right image, and so until the 7th pixel. The 7th pixel is matched with the 9th pixel on the right image, and so on. In order to apply dynamic programming, or in order to learn how it works, first we need a rectified image. We have to rectify the images. Then we will produce a cost matrix, and then we produce optimal path or a minimum energy path, which can be used in order to find the corresponding point, which later can be used in order to find the object coordinates. Let's take an example. As you can see here, this is left image. Sorry, this is left image, and this is right image. Okay, actually, this is the images. Sorry, this is the images. What we will take, we will take one row of the image, just one row. And from the left image, this is the row, a sample of the row. This is pixel value, pixel gray value. For example, this pixel is here, 150, and so on. And this is the right image. This is the right image, okay? We will arrange the images. This is the right image pixel, okay? And this is the left image pixel value. What we will do, for the first row, we just multiply the occlusion. The occlusion has been taken, or the penalty of the occlusion, we have to need to assume a value. We assume 10. What we will do, each pixel we multiply by 10. This is 1 by 10, 10, 2 by 20, 2 by 10 is 20, and so on. Then for the this is for the row, and the left column, this left column, the same, similar. We multiply 1 by occlusion, 2 by occlusion, and so on. For the rest of the matrix, we use the cost formula. What does mean? For example, we will take this image, for example, this pixel value. What we will do, we will compare, first of all, the difference, the absolute difference, 120 minus 203. We will, for example, it will give us 120. It will give us 70. Actually, it will give us 77, and sorry, 83. And we, for example, sorry, this one. Let's start with this one. 120 minus 203. It will give us 83, and 83 plus 10 to 93. Okay, we have from this direction 93, and from this direction cost, this cost I minus 1 plus 10, it will give us 30, and this one also 30. Therefore, the minimum of these three, it will be 30, and so on for the rest. During this operation, we record the minimum value. These are the minimum, and these are the minimum, and these are the minimum, and so on. Okay, the direction, which of them is the minimum, and so on. Okay, later on we will find the for example, along this path we will need to find the corresponding point. For example, the corresponding point for this one is this one. The corresponding point for 100 for the second point is this one. For the third point is this one. For the fourth point is this one. For the fifth point, for fifth point is this one, 200. For these are considered occluded. Okay, now we are going to the sixth point. The sixth point, the corresponding point for the sixth point is pixel number 8. The corresponding point for the pixel number 7 is pixel number 9. The corresponding point, these are occluded also, as you can see here. The horizontal and the vertical are considered occluded. The corresponding point for the 9 is 9, and so on. This is, for example, for just this path. Later on, what we will do, we repeat the same process for the whole image, okay? And then we calculate the corresponding point in order to find the DSM. This is a result. As you can see here, this is the sample of the image, and what we did, we produced a cost matrix, and then along the cost matrix we produced this minimum cost or time mapping. Later on we were able to produce DSM. Actually the effect of the occlusion is very, or occlusion value is very clear. As you can, if it's 10 it will produce like this, but it will be give more penalty to the uh, edge continuities. As you can see, it's sharper the image. These are the DSM for the pentagon image. Okay. Actually, the conclusion, the dynamic time morphing can be used except to produce DSM, but sometimes it can suffering from the striking because it deals with the hyperpolar line. Therefore, it can be manipulated using filtering. It can be used also to identify the depth discontinuities, which can be used in order to detect the building boundary, as it has been explained on the paper building extraction from stereo aerial imagery using dynamic programming, and it's very useful in order to learn about how dynamic time mapping and how it can be used in order to extract buildings. Thank you very much for listening. I hope you enjoyed and it was useful to learn dynamic programming. Thank you very much. Thank you.